All right, guys, I think we'll go ahead and get started. So for those of you who know me, or for those of you who don't know me, my name is Joe. I'm a graduate student here at MSU. Specifically, I do experiments with superconducting qubits. And today I'll be talking about noise and decoherence in superconducting qubits. My goal today is to give you sort of just a broad overview of a couple of different types of noise and a couple of experiments which investigate these things. So the content today will not be very mathematically heavy. There's one little part where we'll have to talk about some equations. But if you want more detail, I can refer you to, I have a couple things referenced in the talk that you might find interesting. Or if you have more specific questions after, since today is the last talk on superconducting qubits for the semester, I'm happy to send out any references as needed. So yeah, so of course, if there's questions during the talk, please feel free to interrupt. For those of you in Zoom, I don't think the audio is hooked up correctly. So if you have questions, if you could just put them in the chat, I think that's probably easiest for today. Yeah, all right. So last week, Cameron gave a really nice talk on circuit quantum electrodynamics, or CQED for short. And I have actually, my next couple slides are sort of a lightning quick review of circuit QED. So we're all sort of on the same page. And next week, like I said, we won't be talking about superconducting qubits anymore. Camille Michaelis is going to be giving a talk on electrons on helium, which is more towards the special topics side of the semester. So if you're interested in some like really neat systems which have potential applications in quantum computing, I think next week will be really great. And I've even included a little schematic that I found on Wikipedia of what she'll maybe be talking about. Sort of the last bookkeeping thing for today is you can follow the Twitter and YouTube accounts. So the Twitter account tweets out information about the seminars, and all the talks are recorded and are on YouTube for this semester, last semester, and then there's a couple from some previous semesters as well. All right, so before I dive into the review of last week, does anyone have any sort of bookkeeping questions for moving forward, or we're all good? We're all good. Okay, awesome. Okay, so last week Cameron talked about circuit quantum electrodynamics. So just a very brief review. What we do in our lab at MSU and several labs, well, many labs around the world, is we take this thing called a 3D transmon qubit, which is two big antenna pads, which just form a capacitor, and there's a Josephson junction in the middle, and we couple the dipole moment of this device to the electric field in a microwave cavity. So here's half of a 3D microwave cavity is just a metal box where the boundary conditions dictate the resonant frequency of the cavity mode, and that couples to the dipole moment of this device here. And so off to the bottom right, you can see this is actually an SEM image taken at MSU. I think this is a couple years old, but you can see the Josephson junction is actually this tiny thing here that my mouse is on. So it's the region of overlap between the aluminum. I really like this picture because there's no equations, there's no schematics. This is actually what it looks like. So this is sort of the experimentalists' side of it. And the coupling between these two devices gives us the very famous James-Cummings Hamiltonian, where the qubit is represented as a two-level system, the cavity is represented as a quantum harmonic oscillator, and there's some coupling between the two with some coupling strength G. And this is just basically how fast the two systems exchange excitations between one another. We often operate these in what's called the dispersive regime, which is a certain limit of perturbation theory for this James-Cummings Hamiltonian. And the important part here is the effective cavity frequency. So just the thing in front of the cavity excitation number is now a function of sigma z, and therefore the cavity frequency depends on the state of the qubit. So this might look something like this bottom picture to the right, where the blue curve, for example, maybe represents the cavity transmission when the qubit is in its ground state, and the red curve represents the transmission through the microwave cavity when the qubit is in its excited state. So just based on where this peak is, we can determine what state the qubit is in. So this is great. This is the sort of the hallmark of circuit quantum electrodynamics, and this is what lets us measure the qubit. Okay, and very briefly, Cameron talked about photonic cat states, which are superpositions of coherent states in a microwave cavity. And the reason this is kind of interesting is because now our qubit is not this Josephson junction thing, but is actually superpositions of photonic states in the cavity. And here I've plotted some examples of what the probability distributions for these might look like. And I am of the belief that it's called a cat state because these fringes in the middle look like cat whiskers. Some people have other beliefs, but I read that once, and that's what I'm sticking with. And so these are, yeah, just two representative cat states. And so I want to use actually this fact to lead into what I'll be talking about today. And the question is, why are these cat states useful or interesting? I think they're very interesting from a perspective of fundamental physics. These are highly non-classical states of photons. But what about the usefulness? Why is this useful? Does anyone have any thoughts about what we talked about last time? And maybe, I think this is a very poorly worded hint, but does anyone have any ideas on why this kind of thing could be interesting or useful for quantum computation? Okay. Yeah.
You get like this, it seems like maybe you get this almost just like inherent protected qubit. Like,
yes, that's exactly right. I think Camille bailed me out there and knew what I was going for because did you have a no? Okay. Yeah, so that's right. Because the states are coherent states, they're also eigenstates of the lowering operator, the photonic lowering operator. And so there's some intrinsic protection against errors based on what the state looks like. So these states are very special because the decoherence affects them differently. And so this is, cool, but the question is, why don't we just make better qubits that are protected from decoherence themselves, and then we don't really need to mess with this difficult stuff. So what I want to talk about today is, what is decoherence for a qubit, noise or decoherence? How do we measure it? How do we determine what affects it? And how can we view this in sort of a single type of measurement? Yeah.
What's the thought, or is it like the
Yeah, that's a great question. So this is something called the Wigner function. So it's the quantum mechanical analog of a probability distribution based on the axes here are the real and imaginary parts of the coherent state. So it's like the magnitude and the phase. Yeah, and so the color scale represents, I actually don't remember what's what. I think blue is positive and red is negative. But here I've just plotted two, not random, but two different cat states. And the hallmark of it being a quantum mechanical analog to a probability distribution is that you can have negative values, versus in a classical probability distribution you can't. But since it's a probability amplitude in quantum mechanics, you take the modulus squared. It's so it's something like a probability distribution here. Yeah.
So it has inherent protection against like spontaneous sort of.
Spontaneous photon emission.
Yeah.
Yes. There's so you can use the fact that the coherent state is an eigenstate of the lowering operator and sort of build in this extra protection against single photon errors.
Are these states also more susceptible to phasing?
Yes.
Okay.
Yeah. They are. Nothing's perfect. Yeah. So actually, there's a company who uses cat states as their architecture, and they've been able to get decoherence times, T1 times of hundreds of seconds, but their T2 time is 0. So it's a transistor. Okay. So yeah, I want to very briefly mention the two primary types of decoherence a qubit can experience. And I can't take full credit for these analogies. This actually comes from Google Quantum AI slides. And I really like the analogy, so I'll be using it today. But if you want a more complete description, you can check out Google Quantum AI. So the first type of decoherence is energy relaxation. So if I have my qubit here, which I've represented as a spin, and it has some energy, we can say the qubit just relaxes and emits some energy to its environment and decays to its ground state, which is the low energy state. In the language of quantum computing, this is what we call a bit error. because it's like a bit flip in classical computing. And so our system has some energy and it relaxes to say the ground state, which here is the arrow pointing up, and emits some energy here. We can measure this in the lab. So this is some data actually from our lab at MSU, where we prepare the qubit in its excited state, and we just wait for it to decay to its ground state. And we see the characteristic 1/e decay time for this measurement is 185 nanoseconds, which is not particularly long relative to state of the art, but it is what it is. This experiment wasn't designed to have good T1s. At least that's what I tell myself. Okay, and the other type of error we can have is we say the qubit marches to the beat of its own drum, where its frequency changes. And this is called the phase error, because as the frequency of the qubit changes, the phase of the superposition states also change. The phase is like the frequency times the time. And so here, what this would look like is we have our qubit state with some definite frequency or transition energy or frequency. I use interchangeably, and that sort of fluctuates in time. So the size of this circle, which is represents the energy, changes. And again, this is something we can measure in the lab, where we prepare a superposition state of the qubit and then measure how its phase evolves as a function of time. And the decay constant for this specific measurement is 275 nanoseconds. Again, not particularly good, but it's just what we measured. Yeah. Oh, yeah, that's a great question. So this P of E is the probability of measuring the qubit in the excited state. So it should be bounded between 0 and 1. In this particular measurement, the system's quite lossy, so we don't have a unit measurement fidelity. But that's a great question. So this tau here in this plot is the time on this axis. And so this pulse is called the pi/2 pulse. So what it does is it takes the qubit and rotates it by pi/2 radians on the Bloch sphere. So that's from the one of the poles to the equator. And then if there's no delay time between, we'll do another pi/2 pulse, so that rotates it from the equator to the other pole. And so now we've basically just put the qubit into its excited state. So at short times, we would measure a very high probability that it's in its excited state. And as this time changes, this qubit superposition state evolves around the Bloch sphere. So that's why it would oscillate. Or that's why it would decay. The oscillation comes from the drive. Okay, so these are sort of the two errors we have. Well, of course, there's more errors. These are the two I'll be talking about today. The depolarization and the dephasing. Okay, so one way to mitigate dephasing, I think this was maybe in the 50s or something, the famous spin echo experiment, where rather than measuring the dephasing with this pulse sequence, like I had on the previous slide, where we prepare a superposition state. That was our question. I'm curious to know how you measure the phase in the lab. The phase of, oh, yeah, so that would be back here. So the way we measure the phase is, so we don't actually measure the phase. What we do is we project the qubit state onto either the north or south pole of the Bloch sphere, and then we can infer from that the evolution of the phase. So it's just related to this measurement here. Does that answer your question? Okay. Oh, was there another one? Okay, so what we can do is add in this extra pulse in the middle, which is called the spin echo. And so now if we look at an animation of what happens to the qubit state as a function of time. Oh, sorry, this reloaded. We got to wait for it to start from the beginning. So we'll apply a pi/2 pulse to focus the qubit onto the equator of the Bloch sphere. And then as the system dephases, we apply a pi pulse, which causes all this noise to refocus on itself in time. So there's this dephasing. That 180 is the extra pi pulse, and then all this dephasing sort of undoes itself just by evolving the opposite way in time. And so this is a technique first introduced in NMR systems, which in principle should increase the dephasing time or decrease the dephasing rate of the spin system. Okay, so yeah, I really like this. I think it's a helpful visual tool, but what does a measurement look like? So this plot is taken from a paper which I have the reference to on a later slide. And in their system, they measure a Ramsey decay. So Ramsey is when there's no refocusing pulses of about 2.5 microseconds. So again, not, the time doesn't really matter so much here, but just how it changes. And then with the addition of this echo pulse, we get this, this blue curve, and we see that the decay time increases to 23 microseconds. So that's about an order of magnitude increase in the dephasing time, or an order of magnitude decrease in the dephasing rate, just by refocusing this, this reversible noise with this extra pulse here. So there's a lot of sort of games you can play with fixing dephasing noise, and this is the simplest one. You might ask, what if we add another pulse and refocus more of that noise? It's sort of the next logical question. What if we have 2 pulses, or 3 pulses, or 4 or 5? And in fact, this is the same paper, does that same exercise where they add up to, it looks like almost 100 refocusing pulses here, and it looks like the dephasing time increases with every pulse. So the implementation of many of these refocusing pulses was called CPMG. It's Carr, Purcell, Mayboom, Gill, which is just the name of the scientists who introduced this method here. And so if you have maybe n refocusing pulses, which is just some arbitrary number, this is what your pulse sequence looks like. So you prepare your superposition state, and then in time you periodically refocus this dephasing noise, and then at the end project to one of the poles of the block sphere and measure.
Does this measurably affect T1 in a positive or negative way?
It does not. So T1 processes are different, meaning they couple to other qubit operators.
So, but doing this doesn't introduce extra noise in the system by accident?
It shouldn't. Yeah, it shouldn't. Okay, any other questions here? Cool. Okay, so what does this mean in terms of like the noise the qubit experiences, right? This dephasing process happens from some noise present in the system, which we'll get into a little more detail later. But I really like this plot here, which shows this G of n, which is called the filter function. So it basically determines what type of noise is present on the system. And for n equals 0, so that's 0 refocusing pulses or just a regular Ramsey experiment, the low frequency noise is allowed into the system. And then maybe for something like n equals 10, the low frequency noise is filtered out by all of these pulses. And then noise in this plot, about 5 megahertz is present in the system. And if the noise present is something like 1 over f, which is typical in experimental setups, you actually would get much more noise at lower frequencies and less noise at higher frequencies. So this is why this sort of CPMG filtering procedure reduces the noise in the system. Yes.
So I noticed the higher frequency you have as to like gates, you get more older noises. So that means not higher frequency the better.
So if you can filter out the lower frequency noise, typically that's better for your system. Yes.
So is there like a typical frequency you want to be pursued for?
Typical frequency for what?
For like filter out all the noises.
Oh, yeah. So you can't ever quite hope to filter out all the noise, but if the noise in the system is 1 over f, then there will be more noise at lower frequencies. So you'd like to filter out the low frequency noise. The cutoff for low frequency noise is sort of arbitrary, but sort of the higher you can go, typically, the better. Yeah.
The frequency here is megahertz.
Yes.
Like the normal frequency transition.
Oh, so yeah, the frequency. Yeah. So typically the transition frequency of the qubit, so the energy splitting, in frequency units is gigahertz. Yeah, that's a great question. So depolarization, or like these T1 processes that I talked about, those sample the noise at the qubit frequency, so at like gigahertz, but dephasing typically samples the noise at megahertz or so. So the dephasing noise is typically much lower in frequency. Awesome. Any more questions? Okay, so I've sort of spoiled this slide a little bit, but I want to talk about a little bit about what causes these errors, maybe from something like the Hamiltonian perspective. So we have, maybe just our representative qubit state on a block sphere. There's nothing special about this state. It's just, some superposition. And we have the z-axis, which we'll call the longitudinal axis, and the 2 transverse axes, x and y. So longitudinal relaxation is these processes which drive us between the poles of the blocks here. So we have gamma 1 up, which is the rate at which the qubit is driven. Let's see, in this picture, it looks like from the 0 state to the 1 state, and gamma 1 down, which is the rate at which the qubit is driven from the 1 state to the 0 state. Typically, if your experiment is in cryogenic temperatures, this rate gamma 1 up is almost 0 because there's very little to no thermal excitations with the right energy to drive you between these two states. So oftentimes what we measure, this T1 I called, is just the inverse, approximately the inverse of gamma 1 down. Modulo the very small contribution from this rate here. Oh, these two came in at the same time. Okay, I guess we'll talk about them together. We can have these pure dephasing effects, which is related to what I talked about on the previous slides, which just drive us around the equator of the Bloch sphere with some rate gamma phi. So this is pure dephasing because it only acts in the XY plane. And then we can have this overall rate gamma 2, which we call the decoherence, which is related to the sum or proportional to the sum of gamma phi and gamma 1. So gamma 2 is something like you'd measure in a Ramsey experiment where you have dephasing and relaxation sort of all acting at the same time. Okay, but how do we write these down in terms of like a variable in our Hamiltonian is our next step. Okay, well, I was gonna not have the arrows there, but I guess they're here. So if we have our two-level system as our qubit with sigma z, we'll call our longitudinal relaxation coupling to the sigma x operator with some frequency delta gamma perpendicular. And then this dephasing happens just due to, like I said, frequency fluctuations in the qubit, and that couples to the sigma z operator. So a question I was going to ask, which is kind of spoiled by the arrows, is why would I put a sigma x here? Can anyone maybe take 30 seconds and talk to your neighbor about why it makes sense for there to be a sigma x operator here? And what else could it be? And why is it okay that it's just sigma x? I think this one is a little different. Maybe just a sigma x. No, so here, if you're doing your experiment at low temperatures, you'd have like thermal noise kicking in from the ground state to the excited state. But if it's very cold, those thermal photons have almost zero occupations just from like Bose-Einstein distribution. And so here your relaxation rate gamma 1 is going to be much larger than your excitation rate gamma 1.
That term doesn't care which state.
Which one? Oh, this, yeah, this one, no. This at the Hamiltonian. Yeah. I think it assumes the other one is 0.
That term flips over.
This one does. Yeah.
That's what he said.
It's a good question. I don't know that these two are consistent. I'll have to double check that.
Okay.
But yeah, I see what you're saying. Because otherwise this would have to be sigma minus or yes, yeah, it's a number. Okay, does anyone have any ideas? So yeah.
It's a sigma x because we need to mix the states, so it's got to either be sigma x or sigma y.
Yep.
And there's rotational invariance. So
yes.
It doesn't matter which we use.
Yeah, that's right. And actually, yeah, so Makola had something in the Zoom chat as well, and he said the same thing. It drives the qubit from 0 to 1 or 1 to 0. Like you said, we could use sigma y. Typical notation is sigma x. We could also actually use some superposition of x and y because we just need to be driven from one pole of the Bloch sphere to the other. Sigma x is okay because we have rotational symmetry, and so pick your favorite one. And it's typically easier to work with real numbers. So yeah. This one? So this just represents if we have some fluctuations in the frequency delta omega, it will, so you can imagine if I grouped the first and the third term together, then there would be some variation or fluctuation in the qubit frequency, and that would lead to dephasing of the qubit state. So these two, the second and third term I have on the screen are independent here. So they're two different processes. Yeah, that's right. So the dimensions are different, but we could rescale this delta omega to be frequency per time. And then, yeah, then it wouldn't be correct to call it omega. It would be like delta, I don't know, call it delta H. But it's, yeah, it's right. The dimensions, if we think of omega and omega perpendicular as frequencies, then the dimensions are inconsistent, but the message is the same. Yeah, that's a good, thank you for catching that. I totally would not have caught that. All right. And I saw an answer in the Zoom chat, and those the same as looking for. Okay, so let's sort of revisit the echo experiment from this perspective of these noisy variables coupling to the qubit. So if I have a superposition state of the qubit, it'll have some phase evolution in time, which we'll call phi of t, and we can break that into two parts. This part, which is maybe the deterministic part, which has the mean value of the qubit frequency times the time, as well as this delta phi, which is the fluctuation in the phase due to some external noise in the system. Then the mean evolution of the phase of the superposition state is given by the mean of e to the I omega t. E to the I omega t, which if you assume Gaussian fluctuations leads to this expression e to the chi n, where chi n is this, or e to the chi n is this function here, where this gn is called the filter function, which is exactly what we showed on the previous slide. And gn is given by this expression here, which was what I said I didn't want to discuss today because it's quite the interesting equation. But the important part is this n here is the number of refocusing pulses in the experiment. So these plots I showed before are actually just evaluations for gn for different number of refocusing pulses. And so I think to answer your question about earlier, the frequency would come into, the x-axis basically would come in as the omega argument in this function. Okay, so let me go back one quick. So today, this is all I'll have time for to talk about with dephasing. Like I mentioned, this is by no means a complete description of dephasing in these types of experiments, but I have at some point the reference to this article, which was also linked in the email. Yeah.
Should you think about this as an experiment to expect it, or should you think about it as something that is mitigating noise?
In terms of these filter functions?
Well, in terms of this process of P over N pis. Pis with P over N.
Yeah. Let's see. So your question was, is it something that's set in the experiment or something that mitigates noise?
Let's say a practical situation where you have a gate other than the pi hat, and you some gate, you split it into two, and you want to make it better.
Yes.
Could you do this procedure to make it less sensitive to noise?
Yes. Yeah. So this is one way people will increase their dephasing times or decrease their dephasing rates by introducing some CPMG to hold on to the phase coherence longer. The trade-off is, as you implement more CPMG pulses, the pulse sequence gets longer, and so now you have to worry about this rate gamma 1 also coming into play. So the perfect scenario is you have infinite refocusing pulses, but unfortunately, in an experiment that's not.
And does it matter if you have multiple qubits that are coupled together, like independent?
That's a good question. I don't think I know the answer off the top of my head, but I can give you a guess. Typically, if you have two qubits interacting, you'd want them to be detuned in frequency. And so if they're detuned sufficiently relative to the bandwidth of these pulses, then pulses on one qubit shouldn't affect the other qubit. That being said, you'd still need to worry about turning on the interaction by tuning them into resonance. And so you'd need a variable coupler versus a static coupler, I think, for this to work best. But like I said, that's just my sort of off the top answer. Oh, there's something in the chat. Oh, thanks, Camille. All right, so like I mentioned, that's all we'll be talking about for dephasing today. So I want to talk about depolarization now, very briefly. And this one, thankfully, well, maybe not thankfully, depending who you are, we can't use these CPMG pulses to help. This is because these energy relaxation processes are typically not reversible. But because we have no refocusing pulses, it's a little easier to write a more complete mathematical description since we don't have to worry about the number of pulses we have. So we can write the interaction Hamiltonian between a qubit and its noisy environment as follows here. So nu is the strength of the interaction between the qubit and its environment. O is just some qubit operator. So for a T1 process, this would be like sigma X or sigma Y or whatever we said. And lambda is the noisy variable. Maybe it could be like a fluctuating charge in the environment. And we'll define the power spectral density of the noise as S of omega as equal to the Fourier transform of this thing in the blue box here, which is called the autocorrelation function. And to give some intuition about the autocorrelation function, it essentially asks, is the noise at time 0 correlated with itself at time t? So for example, the simplest autocorrelation function I can think of, or the example I like is, say lambda is sine and tau is 2 pi, then the autocorrelation would be 1 because sine is periodic in 2 pi. For example, if you have two things that are totally uncorrelated, the autocorrelation function would be 0. And then the power spectral density essentially picks out the important frequency components of the correlations of the noise. Okay, so this is a useful quantity for talking about noise in T1 processes. Yeah, and so lambda of this correlation just asks if lambda is correlated. Okay, and so S of omega, it turns out, is actually related to the emission via Fermi's golden rule, and it encodes information about the emission or absorption of the system into its environment. So typically we would say S of omega at positive frequencies represents the spectrum that the qubit emits into, or the quantum system emits into, and at negative frequencies, it would represent the qubit absorbing information from, or absorbing energy from its environment, rather. And so we can plot sort of some important types of noise for quantum systems. We have this 1 over F noise. Oh, chat. Oh, sorry. We have this 1 over F noise that I mentioned is quite common in experiments. And this is actually symmetric in frequency, about 0. So this means the qubit absorbs and emits energy. The same for 1 over F noise. We have Johnson noise, which is just thermal. And then we have quantum Nyquist noise, which importantly is not symmetric about 0 frequency, because this represents the qubit emitting into its environment. So that one would only be defined for positive frequencies, because positive frequencies correspond to emission. Okay, so this S of omega for a given noise variable will tell us about how the qubit emits or absorbs energy as a function of frequency. Okay, so like I mentioned, lambda is a noise source which couples to some qubit operators. And you might think if the qubit will emit or absorb energy, the noise spectral density at the qubit frequencies might be important, because that would represent the qubit giving off energy at its frequency, meaning decaying like I had on the first slide, or maybe absorbing energy from something else in the system. And it turns out you can go through a long, lengthy calculation, which I won't detail here because I didn't want to take the whole hour doing a single calculation. But it turns out that gamma 1, or the rate at which the qubit emits excitations, is given by this matrix element squared times the noise spectral density at the qubit frequency. So if there's a low noise spectral density at the qubit frequency, this rate is small and the qubit has a long lifetime. So you could think about maybe engineering the functional form of S of omega to shape the qubit loss, which is actually something we do in our lab and is done in many other labs. So question for the audience, this sort of looks like what equation from quantum mechanics? Any guesses? Yes, this is an equivalent statement of Fermi's golden rule. So we have the coupling matrix element squared, and then this S of omega, you could think of as an analog for the density of states with which the qubit can decay into. Okay. All right, so let me go back. So this is, roughly what dictates qubit decay is this noise spectral density, or like I said, we could think of it as the density of states with which the qubit can decay into. And so that would dictate essentially T1 as a function of frequency. And like I mentioned, or like I promised earlier, this is the reference with which discusses a lot of this noise and decoherence and superconducting qubits that I've talked about. like I said, I only had a chance to talk about some of it today, but if you're interested, you can check out this article in the archive. Okay, so now I want to actually very briefly talk about an experiment which sort of investigates this change in the qubit decay. So this is a picture of the experimental setup, and I again have a very brief review of circuit quantum electrodynamics here because I think it's, you can't see it too many times, and maybe it'll make some sense now with a picture of a circuit. So this bottom part here, this cross, is actually the capacitor pad for the qubits, or for the qubit. Sorry, this is a single qubit. And then down here, you can't see it, is a Josephson junction connecting the capacitor pad to ground. And then this tuning fork thing is the harmonic oscillator or the resonator. And then this line up here is just a feed line, which is capacitively coupled to the resonator. So by measuring transmission through this top line here, we could measure the cavity. And then depending on the state of the qubit, we would measure a shift in the cavity's frequency. This is just a brief picture of what the experimental wiring looks like. So this takes place in a dilution refrigerator with base temperature of about 10 millikelvin. There's attenuation going down the fridge to make sure that the signals we send into the system are very small, to sort of preserve the quantum mechanical nature of the system. These are just filtering to make sure we don't have any unwanted frequency components. And then we have more filters, and then we have these isolators, which make sure thermal excitations don't come down this line and accidentally excite the qubit. Yeah.
You said cavity here, but I don't see a cavity.
Great question. So this constitutes the cavity. So this is in a 2D geometry. This is it's called a λ/4 coplanar waveguide resonator. So the previous picture I showed you was a 3D metal box. This is what we would call a 2D geometry. So the cavity is just defined by the boundary conditions implied here and here. And so there's a fundamental excitation, electromagnetic excitation. Yeah, and so the isolators make sure no thermal excitations leak down and excite the qubit. And then we just measure the transmission through this circuit, and that'll tell us information about the qubit state.
Getting a bit off topic, so that's a λ/4. Effectively, it's an antenna, because that's just a copper trace on like a normal piece of right?
Yeah, so this is aluminum. Maybe it's niobium, I'm not sure, but
Do you
some.
need to worry about coupling to external noise things. It's almost a perfect antenna in that case.
It's a great question.
I don't know what the frequency is.
So yeah, this is probably going to be in the gigahertz range.
So it's pretty noisy.
Yeah, I think the filtering will help you with that. I think that, yes. So sorry, yes, that's right. So the filtering makes sure, so this is BPF is a bandpass filter. So it'll let only frequencies or signals of certain frequencies through this. You could think of it like you have a cable and you put a piece in the middle. Only certain frequencies get through here.
Yeah, but that's not one of the actual cavity.
Right, but down here everything's cold, so there should be no thermal excitation of anything.
I'm not thinking, so like Wi-Fi is 2.4 gigahertz.
Right.
That's gonna go.
Yeah, so this superconductor, so these shields here are supposed to. That being said, I have absolutely measured Wi-Fi in an experiment before. We thought it was like some resonance with some mechanical thing, and then we unplugged the Wi-Fi box and the signal went away. So yeah, but in principle, this superconductor should shield you from external things coming in. Yeah.
What's the echo load?
So that is so it's a magnetic filter, which acts as a low pass filter. So what we use those in our experiments as well. You take basically a box and you fill it with this material, which has all these magnetic moments and filters out noise at certain frequencies. So again, it just acts to clean up the signal as it comes down the line. Yeah, but sort of standard. Okay. Yeah. So these experiments essentially measure T1, which again is the qubit energy relaxation rate over. This is about 72 hours. So my guess is Friday morning they clicked play on some Python script and took a long weekend, and then came back Monday morning and saw what their data looked like. And so they see, okay, they certainly are coupled to a noisy environment because the qubit's emitting energy. Otherwise, you'd have an infinite T1. But importantly, it undergoes these discrete, especially if you look at this dark trace, it undergoes these discrete jumps in the time or correspondingly the rate, meaning that not only is your qubit coupled to some noisy environment, this noisy environment is changing in time. And importantly, we need to look at this in the time domain, because if we look at the distribution of these fluctuations as a function of time, we can't really see these jumps. We just see sort of a Gaussian distribution, which is maybe something like what we would expect. So by looking at these fluctuations in time, we really get an idea of how the qubit is coupled to its environment and how that coupling changes as a function of time. So if we look at each individual trace, so each individual dot here is the 1/e lifetime of one of these traces on the y-axis here. So essentially we take, maybe this, both of these are kind of bad, a line cut here, and we fit it to an exponential decay, take the lifetime, and that becomes a dot here. And the authors in this particular experiment are actually able to measure this changing coupling to the environment in a single measurement. So if we look at this measurement here, which is iteration number 207, so it's this trace in this box here, the qubit is decaying quite quickly, and then its coupling to its environment changes, and then its decay becomes longer in time. So they're able to measure, one of these measurements probably takes, say, 5 minutes, and so this coupling is varying faster than 5 minutes. Even kind of more interesting, which is unrelated to most of what I've been talking about today, sometimes this coupling to the environment can be so strong that the qubit emits an excitation and then actually gets it back. So this trace here, the qubit decays, it's emitting excitation, and then all of a sudden the probability of it being in the excited state jumps back up. And so this indicates something we would call like resonant or coherent coupling to some defect in the system. And this is quite interesting. This doesn't happen very often. More so you just measure the qubit lifetime getting worse as it couples to things. So looking at these traces really tells us about the fluctuations and the statistics of the noise and the decoherence in the system. And so we talked about the power spectrum before being an important metric of how the qubit emits excitations. And so the authors calculate the power spectrum of T1. So basically, what are the fluctuations of T1 in time? They measure this dependence here, which can be determined, or which can be found to be due to these two Lorentzians, which indicate that there's maybe these spurious two-level systems in the environment the qubit's exchanging energy with, which maybe isn't so important for today, but importantly, it allows the qubit to act as a sensor for the fluctuations in the coupling to the environment just by fitting to these functions here. And if you're interested in this, I honestly thought I would have less time, so I didn't go too much into it. You can read the paper published in NPJ Quantum Information. Is a really nice paper. So this basically allows us to take our qubits and operate them as sensors for coupling to these like two-level systems or charge traps in the local electrostatic environment, and determine from this data, they're actually able to determine how long it takes the charge trap or the two-level system to jump between its two quantum states. And I forget the number, but I think it's something like 10 to the 4 seconds or something here, which is approximately consistent with how long it takes to undergo one of these jumps that happen on the scale of several hours. So yeah, so that's actually everything I have for today. Is a little shorter.
Other than just, investigating for purposes of understanding what's going to decohere my qubit, is there something people are trying to more deeply understand and using this qubit as a sensor for these environmental fluctuations?
Yeah, that's a good question. So here, what we've talked about today is just coupling to, this would be coupling to sigma X. So it represents how my qubit is coupled to a specific operator. And you can devise other measurement schemes to couple your qubit to other operators and measure how they fluctuate in time. But the important thing is, if you have any quantum system on some chip, there's going to be things that interact with it and things that decohere it and things that take energy away, things that give energy to the system. And if you ever want to realize, a functional fault-tolerant quantum computer, you need to understand how these processes happen and try to either mitigate them or learn to live with them.
So like being able to understand them to cancel them out in some way or get around.
Yeah, that's one way of saying it. So another really interesting field of research, which I haven't talked about today, is what can happen is cosmic rays can hit a qubit chip, which is kind of like, how does that happen? And it can actually cause correlated errors between qubits. And that's, a very in-depth field of research, which if anyone has questions about, I'm happy to talk about after, but I don't have any slides for that today. So
Is there any discussion going on about using something like this as like a co-processor, if you will, to measure the noise of the system next to your actual quantum simulator and actively?
So not that I know of, but I'm not saying no. That seems like a very reasonable thing, but off the top of my head, I'm not aware of any efforts to do that. But I think that sounds certainly like something that's important. All right. Well, if there's no other questions, thank you guys for coming. Yeah, next week will be too much. Right. Awesome. Thanks, everyone.